Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over esters and basically the reactivity of esters, right? So we're going to follow the same pattern that we did with acyl halides and acid anhydrides, but as we'll see, as we go closer and closer to the end of this chapter, there are less reactions to learn, right? So if you look over here, this is our global map that we built, right? The general flow of things. And remember, because you can't make an ester become anything that's above it, we can rule out this guy here, that guy there, and that guy there. This could never become those things above it, right? So really it comes down to just ester becoming a carboxylic acid or ester becoming an amide. And that's the two things that it can do in addition to becoming a different type of ester. Okay, so now that we have a little bit of a idea about the types of reactions that we can go through here, I want to kind of incorporate a new term that I think would help you. So when we talk about turning, let's say, Z into a carboxylic acid, right? What we need to add to this, and I hope you could see right away, is something like hydroxide base or water in general, right? Water with acid or base. Now, what if we wanted to turn it into, let's say, an amide? So then we would need nitrogen, right? So, and it could be NH2 or NH3 or NH2R and so on, right? Some kind of nitrogen that has at least one H to remove, right? That's what we learned about with the acyl halide section. Now, what if we wanted to make an ester? So then in this case, we need an alcohol, ROH. What if we want to make an acyl halide, right? So then in that case, we need SOCl2, which we'll talk about again soon. What if we want to make an acid anhydride? And so in this case, we're going to use carboxylic acid. Now, it might be in the base form or the acid form, but this is generally what we're looking to do. So I want to give you, this isn't new, right? This is kind of, what we're doing is we're seeing that whatever this is on the right, we're just putting an extra H, and that's what is over the arrow. So NH2 is NH3, OR is HOR, OH is H2O, right? So, and this is exception, this is SOCl2. It's not HCl, basically. That's not what we're going to do there. And we'll learn about that soon when we get to carboxylic acids in the next video, the next section of theory. And then finally, acid anhydride, so we need to add this in, so we're going to have an H on it, right? So this is basically a quick way to identify what you need to add. Now, the last thing I want to point out is the name of these reactions. So when you add water, we call it hydrolysis because we're breaking this bond, the Z bond, with water. So lysis means break, and we're using water to break, hydro. So if you want to use an amine, we call it aminolysis. Aminolysis. Okay? Alcohol is called alcoholysis. Alcoholysis. And this one doesn't really have a name that we could think of. It's just using thionyl chloride to make an acyl halide. Nothing. And the same thing here. It's not like carboxylysis or something. I've never heard of that. So really, it's just these three up here that we have some kind of friendly name for. I mean, you know, we could say carboxylysis, but I've never heard that. I don't think it sounds natural as you say it. So these are the three that I want you to know about. Okay, so I decided to add this in now instead of in the theory part when we first began section 1, because now you have a better sense of how this works, and so it's better for me to add a little bit more terminology now than doing it in the very beginning where it wouldn't be as meaningful to you. So you've seen enough that this makes sense. So if I say go through hydrolysis, then you know what that means, right? It means water, or alcoholysis, or aminolysis. You now have an idea of what that means, right? And now you know when you use them. Okay, so let's continue. And in this part of our journey, we're now at the ester. And so we're going to become either another type of ester, and that's called transesterification, meaning you're changing from one ester to another, or carboxylic acid and amide. But remember, you can't become anything above, right? So you can't do that, you can't do that, and you can't do that, right? So none of that stuff above. I'll just keep it nice and clean. All right, so let's get started. So let's start with, I guess, let's start with, I guess we'll start with hydrolysis, right? So number 1, or A, let's do hydrolysis. And so now, by the way, the same terms, hydrolysis, I could use this now back in the acyl halide section or the acid anhydride section. I just decided to teach it to you now, the term. You know the reaction, it's just a term now, right? So now you know what hydrolysis means. It means water, breaking with water. So if I have an ester, there are two ways to do this, okay? So actually what I'll do is I'll number this 1, and then A will do acid pathway, acid catalyzed. Okay, and so what that means is obviously we have an ester, let's say OCH3, make it simple, and we're going to add acid to it. So H+, it could be H3O+, H2SO4, any acid that we can think of, H2O, that's relatively strong, right? So H+ is always the same things. It's either H3O+, which is always what you think of by default, H2SO4, HCl or HBr, HI, something like that, right? Actually, let's say HI, that's a little bit stronger than HCl, but it could be HCl, it could be HI, HCl, okay? Also, it could be things like NH4Cl. That's new, right? Something different. But I think you know where that came from. I remember with the amide, when you made this from the amide reaction, when you converted acyl halide into an amide, right? So this is an acid. That nitrogen is really positive, Cl's negative, so that the nitrogen's positive can act as an acid and just protonate something. Okay, so there are many acid types. Don't get too caught up in that. Just recognize, if anything, NH4Cl is new. It's something that we haven't discussed until now. So that is a good acid, and it's something that we made during this chapter, and we learned how to, okay, or how it happens. All right, now anyway, so I'm going to use H+, whatever it is. I'm going to protonate just as we always do, making this positive. And now the next step is going to be where this opens up, right? And then water is going to come in. Now here's the key. We're about to come to a very important intermediate, which is no different looking than what we've been doing, right? So instead of OR, we've had Cl here, an acid anhydride, but now we have this. And here's the key. This is so important. Notice that what's coming in is the same atom that's already on there and there, right? So what we really have to do is these two are the same in leaving group potential. So they both have the same potential, because if you go back to the very, very beginning of our discussion in section 1, we said that water and alcohol have the same pKa, roughly, right? So that means they have the same leaving group potential. So if this was to close down, then really the one that's going to leave is the one that's positive. And that's simply because they have the same leaving group potential, oxygens, and so the one that's positive is the one that wins. Okay? So remember how acyl halides and acid anhydride, it didn't matter if it was positive, the Cl, or the carboxyl group. It's still left, right? But not here. In this case, you have to do a proton transfer. We must do a proton transfer. This isn't an option. You have to do this. If you want the OR to leave, then you have to transfer the proton. So we go like this. We go here and pull that H. And now we have the one that we want to leave ready to go. So we have an OH here and we have an OHCH3. Okay, very important step. Okay, so this is critical. It doesn't sound like a big deal. It's really not, but I want to emphasize it enough that it just sticks in your brain. So you must do the transfer of a proton, unlike acyl halide where it was optional. Okay, and actually you didn't do it. So here you do. Okay, now the next step is this is going to close back down and this is going to leave, and so now we get to double bond O with an H plus OH, and we get to OHCH3. Okay, so now we've got our traditional alcohol leaving group because it was an ester, and we made a carboxylic acid, but we're not done. It's not stable. So the last step is to do a minus H plus, meaning I don't care, maybe a base pulls it off from here, or maybe whatever H plus was, the conjugate base does it. It doesn't really matter what does it, right? So I'm going to write some base pulls off an H, and you're done. You're at the end. OH plus CH3OH. All right, now I could have done that over here, right, over the arrow. I could have wrote step 2 minus H plus, and I wouldn't have to draw it again. But I want to show it to you since this is the first time we're talking about it, so that's why I showed it clear right here. Okay, so that's the mechanism, and so nothing really new other than the fact that you must very important, you must do a proton exchange or transfer. You have to do that because that's how you know who's going to lose.